That is Beth Shapiro, Colossal Biosciences Chief Science Officer, standing over a cattle jaw that has been baking outside in the Texas sun. She says it with the flat confidence of someone who has drilled into thousands of bones, because she has. And the technique she is demonstrating, messy and almost comic as it looks on camera, shares its exact fundamentals with something else entirely. A discovery made by a completely different team on the other side of the planet that read DNA roughly 2 million years old, older than any bone anyone has ever sequenced. Old enough that it broke a boundary scientists had drawn on paper years before anyone actually tested it. Start with what Shapiro is really doing, because the demo is more careful than it looks. She picks the bone itself over the surrounding tissue and teeth, because bone tends to preserve better. She lays down foil, puts on gloves, and cleans the surface with a rotary tool before cutting into it, and she is explicit about why. Every bone that has spent time in the ground has picked up bacteria and fungi, and every bone she has personally handled now carries her own DNA on the surface too. So the first job is not extraction, it is subtraction. Dust away everything that does not belong before you ever touch the part you actually want. She uses a rotary tool fitted with a diamond cutting disc, the kind that can shatter mid-cut and go flying, which is why she wears safety glasses and tells you plainly that you should too. By her own count, she has drilled into thousands of bones over the course of her career, enough that she calls herself a bit of an expert, and it shows in how unbothered she is by the noise and the mess. Then she cuts slowly, on purpose, because friction generates heat, and heat is one of the fastest ways to destroy the very thing she is trying to preserve. The sample goes in a bag. The bag gets labeled because an unlabeled sample is a sample you have already lost. Then it travels to the paleogenomics lab at the University of California, Santa Cruz, where it gets ground into powder, dissolved, and sequenced. None of that is flashy, and it was never meant to be. It is closer to a cooking show than a breakthrough. But strip away the humor, and what is left is the entire discipline that the whole field of ancient DNA rests on. Avoid contamination, avoid heat, label everything. Wait, that discipline scales. It works the same way whether the bone is a few years old or a few thousand, and that raises the obvious question nobody answers on camera. How far back does it actually reach? How old can a piece of DNA get before there is simply nothing left to read? Here is where the story stops being about technique and starts being about physics. DNA is not indestructible. It is a molecule, and molecules break down at a measurable rate, the same way a radioactive isotope decays on a predictable schedule. In 2012, a team led by Morten Allentoft and Michael Bunce published a paper in the Proceedings of the Royal Society B that put an actual number on that decay. They studied 158 dated moa leg bones, fossils of the same giant extinct New Zealand birds, recovered from sites that averaged around 13.1 degrees Celsius, and they measured how the DNA inside had fragmented over time. What they found was a half-life. Roughly every 521 years, half of the remaining readable DNA bonds in a sample break down and become useless. Not half the DNA disappears, half of what is still intact stops being intact. That is a brutal kind of math because it compounds. After one half-life, you have half. After two, a quarter. After 10 half-lives, a little over 5,000 years, you are down to 1/10% of what you started with, and it keeps thinning from there. So the team did the obvious next thing. They asked how long DNA could survive under ideal conditions, far colder than the sites they had actually measured, something closer to -5 degrees Celsius, the kind of deep freeze you would find in permafrost. Their model predicted that even in that best-case scenario, DNA would eventually fragment into pieces too small to sequence at somewhere around 1.5 million years. That number got repeated everywhere afterward as though it were a wall, a real, tested limit on how far back science could ever see. It was never that. It was a projection on a graph, built from a formula, extrapolated far past anything the researchers had actually measured in the ground. Nobody had drilled into a 1.5 million-year-old bone and confirmed the model was right. It was the best honest guess anyone had, and honest guesses are exactly the kind of thing a field eventually outgrows. Here is the part that quietly rewrites the story, and it has already happened more than once. Before the mammoth, the record belonged to a horse. In 2013, a team that included Ludovic Orlando and Eske Willerslev sequenced DNA from a horse leg bone pulled out of permafrost near Thistle Creek in the Yukon, and dated the animal to somewhere between 560,000 and 780,000 years old. They did not get that age from testing the DNA itself. They got it from the ground the bone was sitting in, from layers of volcanic ash, and a known flip in the Earth's magnetic field that happened roughly 780,000 years ago, both acting like a calendar buried in the dirt above and below the fossil. That horse held the record for 8 years, and it held it as a rough draft, a genome sequenced at barely enough depth to be usable at all, from a single leg bone a geologist named Dwayne Froese happened to spot in a placer mine wall. Then, in 2021, a separate team led by Tom Vandervalk sequenced DNA from a mammoth tooth and pushed the record for oldest recovered animal genome back to somewhere around 1.2 million years, with some estimates based on the molecular clock stretching closer to 1.6 or 1.7 million. That alone was already remarkable. A genuine sequenceable genome sitting almost within reach of the model's supposed ceiling. But it was still, structurally, the same kind of find as Shapiro's cattle jaw. One animal, one set of bones, one genome. Then, in 2022, a team led by geologist Kurt Kjær at the University of Copenhagen published a paper in Nature describing something stranger. They had not found a spectacular bone at all. They had found DNA sitting directly in ancient sediment at a site called Kap København in the far north of Greenland. And when they dated it, the material came out at close to 2 million years old, older than the mammoth tooth, older by a wide margin than the 1.5 million year ceiling the 2012 model had drawn. The field's own textbook limit had already been broken before most people had finished repeating it as fact. What makes Kap København stranger still is that it was never one animal's genome. It was environmental DNA, sometimes called cDNA, meaning trace genetic fragments shed by many different organisms over thousands of years and locked into the sediment itself, the way sand settles in layers at the bottom of a lake. Reading it did not reconstruct a single creature. It reconstructed an entire lost ecosystem. Forests that no longer exist that far north, insects, traces consistent with a relative of the mastodon, wandering a landscape that 2 million years ago looked nothing like the frozen coastline sitting there today. Kap København right now is barren Arctic ground that supports almost nothing. 2 million years ago, according to the same DNA, it was closer to a boreal forest, which means the coldest, most lifeless place on the trip north turned out to be sitting on top of the warmest secret in the whole story. None of that DNA comes back out as one continuous readable strand, the way a fresh blood sample would. By the time you are down past a few 100,000 years, what survives are fragments, often no longer than a few dozen genetic letters at a time, snapped apart at nearly every point the molecule could break. Reading something like that is less like reading a sentence and more like being handed a shredded document with only a rough idea of what language it was written in. Researchers line the fragments up against the genome of a living relative, an elephant for the mammoth, a horse for the Yukon fossil, and let the overlaps stitch themselves back into a readable sequence. The rougher the surviving pieces, the more comparison genomes and repeated runs it takes before anyone trusts the result. There is also a specific chemical fingerprint researchers look for to prove a sample is not simply modern contamination wearing an old disguise. Genuinely ancient DNA degrades in a particular pattern at the ends of each fragment, a kind of damage that builds up the way rust builds up on old metal, and it looks different from a fresh, uncontaminated sample under the same test. A team claiming a 2 million year old result needs that damage signature to show up consistently, sample after sample, run after run, or the finding does not survive peer review. It is one more version of exactly what Shapiro was doing with her gloves and her foil. Prove the sample is what you say it is before you trust a single letter that comes out of it, and that scale of claim demands a scale of caution to match it. If contamination is a real risk on one cattle bone in a lab in Santa Cruz, imagine the risk sitting in open sediment that thousands of different organisms have passed through for 2 million years. Confirming a find like Kap København is not a matter of one clean extraction. It takes repeated, independent runs, the same contamination paranoia Shapiro showed on her cattle bone, just running at a scale most labs never have to face. So follow the thread all the way back to where we started. A woman with a rotary tool, cleaning dust off a bone in the Texas heat, worried about her own DNA landing where it should not. That worry, that exact discipline, is the same one that let a team in Greenland trust a 2-million-year-old signal buried in dirt. The tools got more sophisticated. The stakes got almost unimaginably larger. The underlying habit never changed at all. Here is the part almost nobody says clearly enough. The 1.5 million year number was never a wall. It was a guess written down in 2012, and reality had already walked past it within a decade. Which means the honest answer to how old readable DNA can get is not a number at all. It is a moving target, and it keeps moving in one direction only, further back than anyone thought the door could open. Somewhere out there, under ice or sediment, or nothing more remarkable than a stretch of frozen ground, there is very likely something older still, waiting for someone patient enough and careful enough to go looking. The horse held the record for 8 years. The mammoth held it for barely 1. Given how fast that number is falling, betting against the next discovery would be a mistake, not betting on it. While one team keeps pushing the record on how far back we can actually see, Colossal is chasing a very different set of numbers on the other end of that same timeline, trying to build forward instead of read backward. Watch 15 de-extinct mammoth facts that rewrite what we thought was possible next.